Hello, everyone. My name is Mohammad Zariff, and I am an associate professor with the University of British Columbia. And I am the principal researcher in the microelectronics and the sensors at the same university. Today, I'm going to talk about microwave RF devices and their interactions with novel materials for sensing and communication applications. Here is the outline for my presentation. So first I'll talk about why we are talking about RF and microwave sensors, and then I'll proceed with the recent developments and using recent technologies such as artificial algorithms and augmented realities in microwave sensors applications. And I'll move forward with the RF and microwave novel materials and their interactions. I'll carry on with the main focus and concentration about MXene, which is a novel and a new material, and its interactions and integrations to the microwave and RF devices. Then I'll conclude my presentation with the future directions and the research. So why we are using microwave sensors? There are lots of reasons that we should move towards this direction. One of the main advantage of these microwave devices are their non-contact and penetrative sensing capabilities. We know that microwave sensors are operating based on the interaction between the waves and materials. So this interaction, because due to the nature of the interaction, it doesn't need to have a direct contact, and it can happen in contactless, and it can happen even in the non-destructive way. So these devices can provide a good and high sensitivity and accuracy, and they are real time because they are just we don't need to wait for any reaction to happen or something like that. So therefore, the interaction, and they're also label free. So basically, we don't need to put markers and so on for the chain of the reaction. One of the main and interesting things about these microwave devices and microwave sensors, because they are interacting with materials through the microwave waves, and these waves are non-ionizing waves, so therefore they are safe to use and have less to no health complications. From legal perspective, also in comparison to something like optical and visual devices, with microwave we don't need to inform the users about being recorded or existence of the device in the environment, against what we have whenever we put the cameras in a room or in an environment. We need to advise the visitors that there is a camera in place, and so on and so forth. So therefore, from legal perspective, also has less complications. So recent advantages and advances in the microwave sensor. So microwave sensors has been around for more than 20 years, but recently we have seen that there's a boom in artificial algorithms and AI. And using these AI techniques in many different sensor devices has provided lots of interest and bring lots of interest for researchers. From microwave perspective, also we looked into the using AI for the sensing, and we noticed that by using AI algorithms, we can enhance the data processing capabilities. Also, we can provide a fast and precise automated decision-making capability to the device. Recently in my lab, we are working towards the integration of the AI algorithms into the chip, so into the CMOS chip. So that means that we would be able to provide some sort of new devices from microwave perspective, which we call them edge devices or microwave edge devices. And these are interestingly aligned with the new direction towards the 6G platforms and 6G technologies, whereas most of the processing are decided to be done locally by the sensors, instead of just sending everything to the network and to a base station for processing purposes. So it's moving towards the distributed analysis of this stuff. Another interesting development, and one of the recently published paper in my lab also, is using augmented reality for the purpose of microwave sensing. So let's say most of the time when we have microwave sensors, we need to go back to the desk, plot the results, and then we need more and more kind of trained people to understand the result and to understand to understand the meaning of those measurements, and then convert it back to the people for the purpose of decision making. But with the technique that we are introducing here, and that's called augmented reality for the microwave sensors, then we will get a real-time response as the sensor's response to the environmental changes. As an example, one of the work that we have developed in my lab, we put FSS surfaces and then coated with different thickness of the same material or same polymer, and then we start to remove and then make the coating, let's say, thinner and thinner. And here we use an antenna for doing this measurement, and the measurement is completely a passive measurement. So as you can see over here, first of all, we can say that, okay, where this sensor is located, even when it's behind and it's not visibly or it's not directly visible to the user. And the second thing is we can tell just by changing the color, we can tell to the users that, okay, how much of the coating has been eroded and how much of the coating is still existed. So if there is a need for repainting or recoating, they can take those actions and redo this kind of stuff. But mainly about this presentation, I'm going to focus about the RF and microwave nanomaterial interactions. So we know that these microwave devices are mainly operating based on the variation in dielectric properties in their near environment. However, when it comes to applications such as gas sensing or optical sensing, these devices are basically numb, and the reason is the dielectric properties variation due to the existence of the gas in the environment is so small that these devices are struggling to detect the variation and providing a meaningful signal. So in order to solve this problem, we have demonstrated that by incorporating some nanostructures such as vertically standing nanotubes, TiO2 nanotubes, or by adding some polymers such as PANI and nanostructures such as reduced graphene oxides, or by changing the surface properties, making it super hydrophobic or hydrophilic, or hydrophilic, we can engineer these microwave devices to go beyond their capabilities, their natural capabilities, and detect, let's say, gases and visible lights and hazardous liquids and so on and so forth. Towards this developments, we got introduced to a new class of materials, which is called MXene. And MXene is basically a max phase materials, and the layers of max phase materials is more like a break over break and break over break. So max phase materials, that the A element, and A element can be seen in this periodic table. A element has been etched away after the construction of the material, and then it becomes layers of max materials over on top of each other. So this material, after removing the A layer atoms, basically they showed a similar responses or similar behavior as metallic structures, but against the metallic structures that they need to be well casted and so on, they can exist in a solution method. So solution in a solution form factor in room temperature, as an example. Looking into, and this material has been discovered, and mainly lots of focus has been moved towards to this new and novel material since 2011. And different people have looked into the conductivity, electromagnetic interfaces, dielectric properties, and optical properties of this material, and they demonstrate that they have a good capability to be used as a EMI shielding or for photothermal applications and photodetector applications in solar cells. What we did in my team, we started to look into this material and started to think about additive manufacturing methods. So we noticed that, okay, we are using waveguides for a long time, and all those waveguides are mainly fabricated out of metals, especially the 3D waveguides. So we started to think a little bit differently and start to 3D print plastic waveguides. And after 3D printing these plastic waveguides, by just simple method of drop casting, as you see in this video or in this photos, just with the putting this 3D printed let's say 3D printed plastic waveguide inside the coating, inside the MXene liquid, and then just waiting and then drying this after, let's say, a couple of hours, we noticed that we can get MXene coated waveguides, and we compare the weight and the complexity, and we noticed that the weight is at least 9 to 8 and sometimes even 10 times lower than the metallic counterparts, and at the same time we don't have the complexities that we are facing with machining the metal-based waveguides for fabricating them. So that was interesting for us. So we started to look into different devices, different waveguide structures, such as resonators, such as twisted waveguides, such as bended waveguides. So some of these waveguides, fabricating these waveguides using metallic materials is very complicated, and it requires sophisticated machining and so on. But here we just use a 3D printer, 3D printed everything, and then by deep coating these waveguides inside the MXene solution, we got these results. And then what we did simulations, and we noticed that the simulations are nicely fitting with the measurement results. And even we compared these waveguides with some of the metallic counterparts that are available, and we noticed that the results are very, very comparable. But the cost, complexity, and the method of fabrication is much, much easier and relaxed than the metallic counterparts. So we tested and fabricated waveguides at different frequency bands like X bands, KU bands, and KA bands, or especially satellite communications, and we noticed that the results are in acceptable ranges. So the research about the MXene and the integration of the MXene in the microwave devices is still ongoing in my team. We didn't stop on the 3D structures. We just moved forward even with the planar structures, and we successfully have published and demonstrated that even disc resonators or planar resonators can be fabricated out of MXene. And at the same time, just recently, we have demonstrated that by incorporating a structure called kirigami to the microwave devices such as split ring resonators, we can do a little bit of beamforming or relate the amount of the strain on the film to the change in the transmission coefficient and so on. So that demonstrated it's going to open a new doors for both sensing and maybe passive risk surfaces like reconfigurable intelligent surfaces for communication purposes in the future. So this is something that we are still working on it, and we are very hopeful to be able to publish this work soon. But most of these presentations that I had in these couple of slides was very unique, and for the first time that has been demonstrated in the literature using the MXene material. We are still looking for different and other materials like nanomaterials, nanotubes, MXene, a combination of MXene and graphene and so on for enhancing the performance of the microwave devices. So by this, I can conclude my presentation. Thank you for your attention, and I'm available for any question and suggestion. Please reach out to me via the email below. Thanks for your time, and thanks for your attention.